Okay, recap on last session. What we do is that we have a principle of impulse and momentum. So again, what is impulse? Impulse, you deal with force. Every force will give you impulse. When you force and the time will give you impulse. And also, when you look at momentum, momentum is mv, mass multiplied by velocity, you get momentum. And for rigid body, you have one more equation, which is the moment equation, which is I omega. Okay, I omega. And the moment will also generate time, will also generate impulse, where the moment multiplied by time, you will get impulse. Okay? All right. So we have gone through one example previously, which is example 2. We will go through example 3 today. Okay? All right, now example 3, if you look at the question, you have a this body and the object going down. Velocity was given, go down, and then the radius was given. So cylinder B was shown, mass is 6 kilogram. So B with 6 kilogram attached to a cord which is wrapped around a round body, a disc at 20 kilogram, as a moment inertia A was given. So moment inertia at A was given. If the cylinder initially moving downwards, so it tell you this example a bit special because previous example the initial speed was 0, but now the initial moving down in a speed of 2 meters per second. And for chapter 6, chapter 7, chapter 8, you are dealing with rigid body. Remember to include the angular motion. You need to link velocity with the angular motion. Okay. Velocity here is a velocity or speed. So you need to convert the speed link with the omega and alpha. Okay. So determine the speed in 3 seconds. Time was given. So again, time was given. Very high chance you need to use the impulse and momentum equation. Ignore the mass of the cord in this calculation. So before you start, you need to do the free body diagram. Okay. So free body diagram, in this case, you have two objects. So one is, and if you know that this V was pulling down, so the disc will rotate clockwise because of the motion V. Okay, so omega is clockwise, and then A will have radius, and there's a tension cable pulling down, and there's a weight pulling down from A. This is for the first object. And then this object, this was the mount to A fixed pin. So pin will have two components. So every pin have two components, X and Y direction. Okay. Then same with the object B. Object B, weight go down, tension go up. Right? So this is two objects. So the tension cable must complement each other. So tension cable will pull down. For the object width here will pull up. So don't be confused with the direction of the tension cable. Imagine yourself, you are that object. So imagine you are the disc. So a disc, if you're tied to a cable, what do you feel? You feel the rope is pulling you down. So that's why the arrow was pointing down. If you are the object of the this cylinder here, you are going down, but your head was tied to something. So something pulling your head. So the arrow was pointing out. So this is how you determine the arrow. Okay. Yeah, just need to highlight is that for your test 2 and final exam, your location of the force and arrow is very, very important because some of you, I catch 1 or 2 of you in test 1, you just simply draw your arrow and I'll give you marks for that. Okay. But for test 2, I'll be very, very straight for your arrow location. If you simply draw, I will just give you wrong answer. Okay? So just take note on that. Your force arrow can no longer simply put already. Okay? So just take note on that. Then you continue to use the principle of impulse and momentum. Right? So just recall what is impulse, what is momentum, and then this is rigid body. So you have 3 equations. Okay, you have 3 equations. So moment, for the disk, you have I omega. Moment multiplied time, you have impulse because of the moment, and the moment after, I omega. In this case, the question is very kind because A was given. In the test or in the final exam, you need to find what is your IA. Okay? Okay. So because example 3, we already assume you already know how to find IA. We don't want to waste time finding the IA already. Right? The whole chapter, finding how to find IA, the second moment already covered very detailed in chapter 7. Okay? So you use, for the disk, you use the disk first equation. For cylinder, you use the moment impulse equation. Okay? All right. Now, how do you differentiate when you need to use the I omega and moment equation? You look at the motion of that object. For example, the disk. The disk is rotating. Then you are sure link with the omega. So you use the omega equation. But the object, green object here, cylinder here, is going in the linear motion. Linear motion, no matter you use omega, you still get 0. So it's meaningless if you use the I omega equation. So for the one that moving in linear line, or they go up, go left, right in a straight line, you straight away use the one that you learn in particles chapter. mv plus ft plus mv number 2. Okay, so this is how you moving fast. And then the direction also important. This, we have a positive direction. We will follow the motion as a positive because we want to get all the positive value. Cylinder here, we follow the y-axis, the y positive go up. Okay, so then you substitute the value lah. So IA was given, omega we don't know. Okay, then moment T, so moment of A here. So if you want to calculate moment at A, you close at A. So W gone, AX gone, AY gone, you only see T. So T multiplied by the distance here, you get moment. So you get T over here, multiplied by the length, 0.2, and then the dt is 2 seconds. In the question give you, you need to calculate the 3-second answer. So you put 3 seconds here. Same with the IO after. IA was given, omega you don't know. So you just put in there, okay? Then for the cylinder, also the same. Mass you know, velocity you know. But in this case, you get a negative because the V is go down. V go down is negative because your Y positive go up. Okay, so it's important to fix your direction, your coordinate system before you solve. Okay, so that you know where is positive and negative. Okay, Y go up positive. Why the coordinate system is important? Because you're dealing with vector. Vector come with magnitude and direction. Okay, then the FT, the impulse. What generate impulse? You look at the diagram, you look at the cylinder, you actually have two forces, right? This is focused on cylinder only. So you just take out the cylinder. So cylinder here, you have two forces. So once you have force, it will generate friction. It will generate impulse. So you have T multiplied by 3 seconds. positive because go up. And then y negative, your W is go down. That's why you get negative. Right? Then what is MB? MB is a last one, so it's still negative because it's going continue to go down. They continue to go down. So if you have these two equations, first equation give you still have one unknown, omega 1, omega 2. The second one, you have V2. Okay, you have V2. Once you have V2, you can calculate the omega of this because this rope was tied to this, and V equal to omega R. V equal to omega R. So once you find this one from the second equation, you take this one, V equal to omega R. So you find your omega R. Okay. So V equal to omega R, you rearrange the equation, omega equal to V divided by R. Okay. So omega 1 is omega 1 equal to V divided by R. So before, this one was not start from rest, but it start with the initial speed 2 meters per second. So you put 2 divided by the radius, you get 10 radian per second before start. Then after start, you don't know. So you still substitute VB here. You still get unknown here. So here, you substitute this one in here, substitute with this one in here, you solve for your VB. Okay? So you get your VB. This is how you solve the question. All right? Now, the difficult part, most of the time I see for chapter 8, when you do chapter 8 question, you will, I don't know, somehow, some of your brain, you will focus on external forces. You will forget about W. You'll forget to put W in your free body diagram. All right. Another thing is that your positive, negative, you will, some of you, not all, some of you, you will miss out the negative sign in your calculation. Okay. Okay. So this is the first method. You can use a second method also. Second method, you combine everything as one system. Right. Same with the example 2. Second solution, you combine the whole system as one. So you cancel the T here. Right? Okay, so this one you can look lah. So it's still the same lah. You just combine the system. Okay. So before, you just in principle of angular impulse and momentum. So the first one is angular momentum. You have I omega 1. You get before. And then the impulse that you have, impulse is you take all the forces you have inside the system. You have the weight, you have the pin forces, and the W pulling down. Again, if you use solution 2, there's no tension already. You see as one body. Then the last one is the end results of the object, which is you will rotate. Moment give you I omega 2. So you solve for all these equation according to the one that you learn. Okay, the detailed calculation was given on the slides. Okay, you still get the same answer. Right? In final exam, you will be forced to use a certain equation. Okay, now you will be forced to use a certain equation. Same like test 1, I saw some of you do not follow instruction. That's why some part of you get 0 marks, even though you get the answer. I give you 0 marks, and I write beside the answer, not relevant, or not following instruction. Right? So just pay attention to the equation or the instruction when it comes to that lah. Okay, once you learn about the principle of impulse and momentum, same with particles, we cover something called conservation. Conservation means everything was not changed before and after. And we do not observe, we don't care about anything about internal things. We want to look at what is after, what is after compared to what is before. Okay. So linear momentum means the object move in the straight line, and then if you're angular, the object will rotating, then you use angular momentum. Okay. Linear momentum means mv1 equal to mv2. The impulse is cancelled because we no longer look at the internal system. Right? Same with angular. Angular momentum means I omega 1 equal to I omega 2. No longer look at moment multiplied by time. Okay. Okay, let's look at, I should take out the thing. Huh? Okay, example 3 is the same. Conservation of momentum. Okay. 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 Now you look at this system. This is but suddenly the surface no longer flat, but there is a like a bumper. So the disc will rotate and then hit the bumper. So the mass was given, the wheel was given, initial IG was given. Again, example 4, assume you already know how to find IG already. When it comes to assessment, you need to find IG. You need to know how to find IG. Huh? Okay, so assume that the wheel does not slip or rebound. Again, I show you in uh, what case, what do not do work. Friction, in what case not do work. You have to be careful on that. Um, Okay, so this do not slip or rebound. Determine the minimum velocity Vg must be. Vg means velocity at here. Okay, velocity at here. It must have just to roll over obstruction at A. So you need to do some calculation so that this object can go over object A or obstacle at A. So you do impulse and momentum because you need to knock knock somewhere, and then it bounce off. So you need impulse and momentum. Okay. So since no slipping, then it will pivot about point A during the contact. Okay. So you draw the diagram before impact and then after. Okay. The G will be here. So first, the velocity will be moving here, mv before the impact. The distance G to the impact A, you take 0.2 minus 0.3, so that the distance will be here, right? And this is the rigid body. So rigid body, you have a moment, I omega. You don't see this one in particle chapter. When it comes to rigid body, you start to see I omega, right? Then when you hit the object already, then impulse will happen. So we hit the object, W will go down. Okay, W will go down. And then some forces were acting on this point. Okay, and this point, when you know that when you knock someone, not something, some point, the arrow will pointing 90 degree to the tangent point or the impact point. And the distance is from G to A. The distance is D. We don't know. We need to find. Right. And then there's an angle there. Right. So in this case, we only see the weight and the impulse, the forces that acting on point A during the impact. Then after you roll over, your mg will go somewhere here, because once you knock, you will like go up like that. Right? You knock, then you go up like that. So then there is again there is a rigid body. Rigid body, you have a momentum to continue to roll. So you have Ig omega 2. Okay. So if you compare the diagram, force at A is much greater than its weight lah. So force at A is much greater than the weight that you have. Okay. So since the time of impact is very short, the weight can be considered non-impulsive. So this is a very special example. So if you have a very short contact, then the weight considered non-impulsive. The impulse force at A has both unknown magnitude and unknown direction theta. You don't know the direction. Here it don't give you the angle. Right? So to eliminate this force from analysis, we take assumption angular moment about A is essentially conserved because of the G multiplied by, because the is conserved lah. You observe is conserved. Okay, then you use angular conservation for angular momentum, right? Or okay, so angular momentum equal to Rm and then V, mv multiplied by the R, right? Angular momentum, momentum is mv. If you need to add the word angular, means you add the arm, mv multiplied by the arm. Okay, and then this one is I omega. You look at this one. So first diagram here is before. You have external the initial momentum and the mv. So mv multiplied by the r plus the I omega equal to here, equal to this one, equal to mv multiplied by the r plus Ig omega 2. So since no slipping, you can use the V equal to omega R to find the omega. Okay. So you substitute this one inside here, right? You'll get this equation. Okay, the rest you can read. So this principle do not apply during impact since energy is lost during the collision. However, after impact, as in figure, it can be used. So we can see during, before, and after. This is the dark color blue is the before. Then the one that on top of A is the after. Okay. So to go up A, the wheel must pass position A. So if VG2 or VG1 is to be minimum, it's necessary that the kinetic energy of the wheel at position 2 be equal to potential energy at position 3. Right? So you need to consider the conservation of energy over here. So when you take into consideration of energy, then you look at potential and kinetic. So number 2 and number 3. Okay, so then you put in kinetic equal to half mv square. Again, this is a rigid body, so you have one more kinetic equation, I omega square. So again, you don't see this one in the particles chapter, but when you come to chapter 6 onwards, you will start to see half Ig omega square. Right? So velocity, potential before is 0, right? Is 0 because this is you put this is your datum. Then kinetic after 3 we'll put is 0 because it's reached maximum point already. Then it's like tumble over. So velocity at 3 start to be 0. Then mgh, potential mgh. Here we use d3. Okay, d3 over here. Okay. So you solve the unknown, you will get the omega. Okay, you get the omega, and then you get the v1. So example 4 is a little bit challenging, right? And I will not ask you this kind of question in your test 2 or final exam. Okay. Okay, example 5. Example 5 is important. It is a very direct application. So here you have a rod here. You have a rod here that pin to O initially at rest. If a bullet, the mass was given, fired to the rod at velocity 400 meter per second at a certain angle, determine the angular velocity of the rod just after the bullet become embedded to it. Means you want to find when the bullet hit this one, meet this one, what is the motion of the rod? Is it rotate or does it what is the velocity of that? So it tell you to find angular and not the normal velocity. Angular means omega. This one you know that it will turn this way. So you make all the motion anti-clockwise as positive in your answer. By logic, you know that this one, when bullet hit this one will rotate anti-clockwise. So make all the direction anti-clockwise is positive. So you use impulse and momentum. Again, when you know that you need to use impulse and momentum diagram, usually there's a meeting point. There's a hit point on that. Okay. Okay. So you draw the impulse and momentum. So rod A, rod O, there's a bullet velocity coming in, right? So momentum mv. So that's why you only see mass and velocity and no other forces. Then impulse. Impulse, you have all the point, and all object you have a center of gravity. So of this one, sometimes you'll forget there's a G point there. There's a center of mass there. All point, you have two forces mount to this one. So again, when you do impulse, remember you include the forces, all the forces at all the point. And some of the careless mistakes when it comes to chapter 8 question, you will, if the question do not give you G, you will forget to include G in your diagram for rigid body question. Okay. Besides the weight, you'll forget the G, the center of mass in your diagram. Okay, so don't do these mistakes in coming test and final exam. Okay, once you have your center of mass, include the omega, include the weight, which is W. But this one you are drawing impulse, so all the force multiplied by time will give you impulse. Okay, so that's why you see forces multiplied by time, forces multiplied by time. A also, the bullet weight, okay, the bullet weight will go down. So why bullet is point A here? Because it say the bullet become embedded to it. The question here, it already tell you what is after. The bullet joined together with the rod. So there is a bullet weight here. Okay, so you need to read carefully. Sometimes maybe your English command is not good. When you read question, you cannot get hold of the question. So this one, it will tell you that a bullet become embedded to it. So remember to include the one that go into lah. Then after you know that principle of impulse and momentum before plus impulse equal to momentum after. So the one that at the last here is only momentum. So momentum, you look at what have changes, right? So the center of mass, and then the B impact point will move to the right. Okay, the G point will also move to the right. Okay, then this is the rigid body, so there's a moment anticlockwise, I omega. Okay, so once you're able to draw these three diagrams, the rest you just apply the equation and you solve for the unknown. Okay, the challenging part is this diagram. Okay, so the impulse of the bullet exerted on the rod, we can eliminate. We don't calculate the impulse of the bullet because the question do not ask you to focus on the impulse. Right? The question asks you to focus on the rod. What happened to the rod? The question do not ask you what happened to the bullet. Okay, so don't overdo the question. Okay, okay. So you see the steps later. We will see as a one system. Here, that's why you see bullet inside the free body diagram. Okay, so the rest is just application of it. The rest you read the note. Okay. So again, you use conservation in this case before angular momentum. Again, what is momentum? mv. If you see the word angular means momentum multiplied by the arm, the distance to the momentum. So you see mv, then times the length to that. So example here. So this is a vector. Vector you can split into horizontal and vertical direction. Okay, so we are more interested that the moment that generate anti-clockwise direction. So here you see we use the cos, mv cos magnitude multiplied by 0.7 from O, so that this one will rotate this way. The one that go down doesn't matter. The one that go down, it will just pull along this axis, so it doesn't give you any moment. Yeah, so this is a momentum. So if you pull parallel, you do not go anywhere. Same with the after, right? After mv multiplied by the distance. Okay. So a left hand side, right hand side, you refer to the diagram over here. Okay. So you have this one multiplied by the length mr multiplied by this one and ig omega 2. Okay, again, this is rigid body chapter. Your rigid body will have a second moment of inertial effect. So you need to include I omega there. Okay, then you solve for the unknown. Okay. Okay, then the rest you just link with normal velocity with the angular parameter v equal to omega r, and then you try to solve for the unknown. Okay, so with this we conclude chapter 8 lah. Okay. Okay, let me stop the recording here.